Good afternoon or late afternoon, everybody. My name is Guillaume Landry. I'm a W2 professor at the LMU Clinicum, so the University Hospital of the LMU. I'm part of the Department of Radiation Oncology, and I lead the LMU Adaptive Radiation Therapy Lab. I'm a medical physicist by training, and my research group is very active in the areas of image guidance, AI-based image processing, with a strong focus that's really towards improving the delivery of radiation therapy. But today I'm presenting not as the head of the LMU Art Lab, but as the speaker of the BZKF Lighthouse Image Guidance and Local Therapies. And I'm thankful for the BZKF to give us the opportunity to let you know what our lighthouse has been doing over the course of the last year. And so let's begin. So the BZKF has established the structure of lighthouses to emphasize certain focus areas in cancer research and treatment. And so we have theranostics, omics, AI, immunotherapy, and preclinical lighthouses. And since January 2025, we now have the image-guided local therapy lighthouse, which is based at the LMU Clinicum. So the goal was to have one of these structures dedicated to local therapies, and our proposal is to bring in advanced image guidance in this domain. So I'll explain to you a little bit more how we see our work. And so local therapies are relatively heterogeneous. They have a few things in common, of course, in that they target specific lesions, and they often do that with the use of imaging. We can have surgery to remove a lesion. We can have radiotherapy to ablate it with radiation or sterilize it with radiation. We have interventional radiology. We have endoscopic or minimally invasive procedures. And all of this is driven by a wide array of imaging modalities. We can be talking about computed tomography imaging, magnetic resonance imaging, positron emission tomography. We have optical images and videos from endoscopes. We can be supplementing this data with histology slides. And so this creates a very heterogeneous array of data for researchers and clinicians to work with. And a drawback of this is that when we need specialized tools for image processing, usually every institution, every group even, will be developing their own in-house approach, which leads to a lot of repeated effort and loss of efficiency. And so one area where we want to bring benefits via our lighthouse is to kind of harmonize the processing of these images and kind of centralize it in the structure of the lighthouse. In parallel, we have very strong developments in artificial intelligence nowadays. So of course, currently the language models are drawing most of the attention, but there's always been a very strong component of vision models. So when I say vision, this is application of machine learning to image processing. And so we have now a lot of models which are typically in the broader computer science world applied to so-called natural images like photographs or videos. But many of these developments are translatable to medicine. And we're seeing more and more cutting-edge machine learning methods applicable to medicine. So we already have some examples. For example, in radiotherapy, we use automatic segmentation of the organs on computed tomography scans so that we can plan how we deliver our radiation more accurately. In radiology, they can use, for example, fracture detection software. And we strongly believe that we can go way beyond what is currently done, and there's a lot of scope for translating these AI developments to benefit patients. And so we think we can improve local therapies at the level of the detection of lesions, the prediction of how they should be treated, and also to guide the intervention better. And so the goal of our lighthouse is to gather BZKF competency in advanced image guidance and to transfer it to local therapies. So this can be, for example, the development of new AI image guidance tools. They don't necessarily to be AI-based, but nowadays most image processing is AI-based. And we also want to generate real-world evidence via clinical testing and validation that these tools bring benefits. So when we establish this lighthouse, which has been running for a year, we set up a few founding principles. So our priorities were the following. We wanted to establish a BZKF-wide network. So not only have people in Munich working on this topic, but we want to link up with the entire BZKF network. And so this is illustrated with these interactions that we have among our groups in our lighthouse. With this network, we want to support image guidance expertise. We want to link with clinical experts as well, not to develop things in an isolation, but do things which are meaningful for our colleagues. And we want to connect to all local therapies. We also want to demonstrate technical and clinical capabilities. So we have set up research projects which try to push forward the use of advanced image guidance in local therapies. And we have, as I said, a kind of affinity for AI solutions nowadays. And finally, it's important that the lighthouse is synergistic. So we want it to be more than the sum of its parts. So it's clear that the projects have to build on each other and deliver something which is not feasible only at one of the BZKF sites. And so to do this, we have reached out to experts across the BZKFs. And so this is our list of principal investigators in the lighthouse. We have a slightly stronger representation from the LMU Clinicum, since this lighthouse is based here. So myself and Professor Michael Ingrish are the co-speakers of the lighthouse. Professor Corradini is representing clinical radiation oncology, Professor Dietrich, MRI physics. We have Professor Wendler from Augsburg, who has a computer science background. Dr. Jan Peken from the TU here in Munich is an expert of AI in clinical radiation oncology. Professor Jana Ute is an MRI expert. Professor Hackel is focusing on hepatic surgery. And Professors Han and Meining from Würzburg are pioneering the use of AI in endoscopy. We have had over the course of the year a few changes due to the natural career progression of our PI. So Professor Corradini is now head of the radiation oncology clinic in Erlangen. And Professor Hütter has left for a university outside the BZKF in Hanover. She has been replaced by Dr. Florian Putz, who's also a radiation oncologist in Erlangen. And so with this team, we are working together towards the objectives that I've outlined. So before we go into the core of activities, I thought it might be good to start with a kind of generalized workflow of how a local therapy can proceed. So this is not a real treatment. I wanted to have something generic so that we can all kind of relate to it. Afterwards, I will redefine this towards some specific treatments. So if in my idealized workflow here, we start with some sort of imaging, right? Some pre-treatment imaging, which we will use to both localize the target and characterize it. On the basis of this imaging, we will want to do some treatment planning. So this can be in radiation therapy, defining how we irradiate the tumor with different beams, for example. Or perhaps this could be deciding on a surgical strategy. Then in an ideal world, just before the treatment with the patient in the treatment room, we can have some new imaging, right, to refine how we plan to treat the patient based on the current anatomy, the current situation of the patient. And finally, we want to deliver the treatment. And while we do this, we want to have continuous image guidance so we can react to during delivery or during treatment possible changes or modifications of the patient's presentation. Now, to tackle the role of image guidance in this workflow, we have set up these projects. So we have classified our projects in 3 pillars, focusing on the detection of lesions, the planning of therapies, and the intervention themselves. So if I start at detection, we're focusing heavily on MRI at the moment in the Lighthouse. So we have techniques for managing the motion of lesions with cine MRI. We have techniques for characterizing MRI on characterizing lesions on low field MRI, and acceleration of MR imaging via AI reconstruction. In the planning column, we have a project focusing on predictive analytics in gastrointestinal cancer. So this is using multimodal data inputs to predict the outcome of therapies and potentially make adjustments. And then in intervention, we have 3 projects. Project P5 in Augsburg focuses on this in-room imaging to refine the patient representation. Project P6 aims to bring AI analysis in endoscopic procedures. And Project 7 focuses on intraoperative liver lesion tracking, so using contrast-enhanced ultrasound during liver surgery to decide how to proceed with the surgery. I will explain each of these projects in turn very briefly in the coming slides. But before we move on, there's also, you notice, a kind of basis to our Lighthouse as well. And this is the core projects. So naturally, we have some coordination of management, which is not very exciting. But what is more interesting is we have a robust multimodal lesion tracker. So this is software which is meant to support the entire activities of the Lighthouse, and I will explain this in more detail. Before we go forward, I kind of rearranged the projects actually into this, let's say, working group representation. And this reflects how, once we started working together, things naturally happened within our group. And so we have arranged ourselves in 3 working groups. The first working group is very similar to the detection working group. So this is the MRI projects grouped together. Then we have multimodal characterization, where projects aim at combining modalities to predict outcomes. And there's a lot of shared modalities between these projects, so they collaborate heavily. And then we have a project which is, we have the projects working on surgical guidance. So I want to start by talking about our core project. And to do so, I find it a bit easier if I introduce a little bit how we do things in radiotherapy, because the first use case for that tool has been radiotherapy. So I need to talk a little bit about hardware here. And so these, what you're seeing here are so-called MRI Linacs. So these are the cutting edge radiotherapy delivery devices we have at our disposition nowadays. And so they combine magnetic resonance imaging with linear acceleration technology, meaning that we can do MRI imaging with very high soft tissue contrast as we are about to deliver the radiation and during the delivery. And so we have such a device here at the LMU Munich, the one on the top here, which lets us do the so-called MR-guided radiotherapy workflow, or online adaptive radiotherapy workflow. And so now we're concretizing a little bit the idealized scenario I showed earlier, right? We start with imaging to do so-called baseline treatment optimization, where we, in radiotherapy, this means we identified the tumor on the imaging and maybe an organ at risk. So the tumor is in red, the organ at risk is in green. And we have optimized the delivery of the radiation from the linac over 360 degrees to give as much radiation dose to the lesion and as least as possible to the healthy organs. Now, as I said, when the patient comes in the room, they go into this device, the MRI linac. Then we acquire a new MRI, which lets us basically re-optimize the treatment. So this was done, the first baseline planning was done kind of offline. The patient went home, this plan was made. Then they come for their first treatment. And while they are in the machine waiting, we re-optimize everything. Once that's done, we move on to the treatment. So this workflow is actually pretty complex, and with the tools available in hospitals nowadays, there's very limited automation. So we need to perform organ at-risk segmentation, target volume segmentation. We need somehow to convert this MRI into a CT. It's not something we will touch upon today, but this also requires some correction. So there are many staff members involved. The median times range from 30 to 40 minutes. The patients have to be patient, literally, waiting in the board before the treatment begins. And so we really believe that there's an opportunity here for AI-driven automation. And this is what drives the research in my research group. And I think this is a good example of how the Lighthouse can bring benefits in general to local therapies. So our tool, this core tool we're developing, is for volumetric segmentation. So I just want to explain a little bit what that means. For many of you, it's probably trivial, but the idea is to segment on a medical image an organ or a lesion, right? So we want to draw these lines around each of the anatomical structures. So this is crucial in local therapies. So we identify our target, obviously, and we can avoid healthy structures that we should not damage by surgery or radiation. Nowadays, this can be mostly automated. So what you see here is the architecture of a convolutional neural network called a UNet, which is in computer science, in the medical computer science area. This is a very famous model. So you can imagine that it encodes information as you go down and decodes it. So it takes the image on the left and outputs the segmentation on the right. And this works very well. So this is an example of segmentation of MR-Linac images for different organs. It's a paper we published in our group a few years back. So you can train these models yourselves. And nowadays, most of the commercial software that we use in clinics to segment organs is also based on this. There are also nice public tools. There's something called NNUNet from the BZKF, which is a self-configuring UNet. So you just throw your data set at it, and it will spit out that you can use to segment your data afterwards. Or we have even things like Total Segmentator, which have been trained on vast databases, which are just working. You download it from the internet, and you can immediately segment your CT or MRI images without doing any training even. So this works nicely for the lung or the heart. But once we move to trying to delineate lesions, then these models start to fail. So there's too much heterogeneity in how lesions present themselves. And there are also cases with microscopic spread, which requires a lot of knowledge from physicians to properly include in the target volume for treatment. And so this calls for a different approach to automatic segmentation. And so this is where foundation models come into play. And so foundation models are, you might have heard about this if you've read a bit about large language models. So these are also called foundation models. This means that a model has been trained on such a large data set that it starts to gain, let's say, automatic generalizability capabilities. And so just like we have foundation models for text, we also have some from imaging. So I'll show you something on the top right here, which is called segment anything model. It comes from Meta AI, and it's been trained on, it's actually like millions to billions of images. And you can see it can literally segment anything. It can be cows walking across a field or cells moving in a series of microscopy slides. And so this is coming from this foundation model ability. And typically these foundation models, even though they are able to generalize, they need to be guided. And so typically we need to prompt them. Prompting means, in the case of imaging, is to usually give very sparse input on the image. For example, we can give a point. I could have clicked on a cow and it would have been segmented, or draw a box around it, or a lasso, which is a slightly more dense structure around, or scribble over it. And while the segment anything model is not really designed for medical imaging, there have been refinements called, for example, MedSam towards that. However, most of them operate in 2 dimensions because most of the, let's say, natural images that we have available for training are 2D. And so this is where this NN interactive comes into play. So this is another model from the DKFZ in Heidelberg, where they took this NN-UNet architecture that I mentioned earlier, and they updated it to include prompts and trained it also on a large corpus of publicly available 3D imaging data. And so what you can do here is that you can provide the prompts and the image to obtain a very accurate 3D segmentation. And so just to put things a bit in perspective, when we talk about segmenting lesions on medical images, so I'm bringing up a MICI challenge. So MICI is one of the leading medical imaging AI conferences. And each year they organize data challenges where people will have access to a data set and try to solve a problem. And what you can see is the Panther challenge here, which is very relevant for us. This was a challenge on pancreatic tumor segmentation in MRI. And accuracy in segmentation is usually reported with a dye similarity coefficient, this DSC you see here. When it's 1, it's perfect. And here you can see we have a score ranging from 0.66 to 0.73, which is not that strong, actually. So in this challenge, they try to do it fully automatic, which I think these results show that this is maybe not the way to go. And so we think it's better to proceed in a semi-automatic way. And so we want to basically have like AI-assisted delineation based on prompts, right? So imagine this is your target. You have a ground truth in yellow. One way of approaching this is that you could draw first a box around it. You get a first rough segmentation. And then you might click one more time to say, actually, don't include this little green island there. It's not part of it. And then ideally, you would be finished with your segmentation and have saved some time. And so what we found is that these types of models, so in this table, we see the DICE score for MRI tumor segmentation. We see that this NN interactive model comes out on top here. So we have DICE similarity coefficient now of 0.85 instead of 0.73. And so you might say, okay, this is still far from 1. But if you look at the literature for the variability among experts to delineate lesions on MRI, you reach values typically of 0.82 to 0.87. So actually, this performance is pretty much on par with experts. So we don't really need much more improvement from this. And so we think this is a very promising way of working. And so I want to highlight a little bit how we see it here. You can watch this video from Florian Putz, where he's segmenting brain metastases using NN Interactive. So here he's using the lasso tool. You see, he just draws a quick outline of the lesion with this lasso tool, and the model does the rest in the background. We get the segmentation in 3D based on a single 2D, let's say, drawing. Here, Florian is not completely satisfied, so it missed a few parts. And so he switches to the point prompt and then finalizes the segmentation by clicking in the image in a few positions. And so with this, he's able to finalize the delineation to his liking. Now he's pleased with the result, and the segmentation process is finished. So we call this a bit like the AI brush. So typically when our colleagues in radiotherapy need to segment GTV. GTV is gross tumor volume, is the nomenclature we use for the tumor. The colleagues need to go slice by slice and do this delineation very carefully. And so we think that instead of doing that, you can use the prompting of foundation models to still interactively segment, but much faster. And so Florian here evaluated how much time we actually save by doing this. And you can see it's quite impressive. It's basically a factor 5. So delineation times went from 5 minutes on average to less than a minute on average. So I think this is very convincing. Of course, the quality is also important. And so they got this DICE coefficient of 0.91, which is very high. And they had blind and experts review the segmentation, and they could not basically tell the difference between clinical or manual segmentation and, let's say, foundation model-based segmentation. And it's also interesting to see because how the interactions were done, because now we have a lot of possibilities, right? We can do boxes, points, lassos, scribbles. And so it turned out that Florian and his colleagues, they preferred to do the scribble most of the time. But this is going to be very user dependent. And so now what we're working on in the Lighthouse is to package this type of approach into a tool which anybody in the BZKF or even internationally can use. So we're working on our so-called core tool. Our postdoc and PhD student are working on an interface. Here I can also play this video. Now the tool is used not to segment a brain lesion, but a lung tumor from a MR-Linac MRI image. And so here you can see that we're again using NN Interactive and going through a series of prompts to achieve satisfactory segmentation. And so what is powerful with this tool is that even though I've showed you mostly MRI images up to now, it's actually multimodal. So you can give it basically CT, MRI, or other modalities, and it will be able to segment in this semi-automatic fashion. It's not only based on this NN Interactive, but we have a whole library of foundation models that users can pick from. The whole thing will be open source and free. And we combine both, let's say, so-called AI brush functionality with classical tools for segmentation that our colleagues typically use. And so we hope this will be a very versatile tool, and we're planning to release it actually very soon in April, so that everybody can now use it. And so this brings me to evaluating this tool, right? So we had some preliminary evaluation from Florian's team in Erlangen, which is already quite convincing. Now we're going to try to broaden that a little bit more. So we first start with a retrospective evaluation. So we have a large database of radiotherapy data available. So together with Erlangen, we will evaluate how accurate we can do this on a broader range of cases, starting with lung cancer patients on CT, and of course, measuring time savings and accuracy gains. And then we want to do this also prospectively. So we want to see how, so I want to point out that there's a big difference in these type of studies between doing retrospective and prospective analysis. So usually once you go to the prospective analysis, when we're starting to deal with real cases, we notice that our colleagues are much more cautious. So we believe it's important to do the validation prospectively. So for this, we have designed a study protocol. It's been approved by the LMU Ethics Committee. We will soon begin the ARTIST study. So using this tool compared to manual segmentation to determine if there are, like, what are the benefits in time saving, and demonstrate that we do not have a negative impact on the final radiotherapy plans that we generate. And so here's a last slide about the core tool. I just want to show how versatile these models are. So these are three selected use cases that we have touched upon, let's say, with this tool since we started working on this. So in the first example here, this is a case of edema following local therapy, where our colleagues administer a drug which reduces the edema, and now they want to quantify how much edema reduction is happening, and they need segmentation of this edema, which is visible on MRI, and this can be done very quickly by using the core tool. It can also be used to track tumors on cine MRI. So in the middle, you see some work from my research lab where we evaluated how accurately this can be used to track the lesion in a video. And we can also have the same thing applied to endoscopy video. So here we're following a lesion in real time during the endoscopic procedure. So this is all based on the same software under the same graphical interface, which I think means shows the versatility of this. And so we hope that with this, we can reduce duplicate efforts in image segmentation. Okay, so I'm perhaps running a little late, so I need to move on. Now I want to quickly show you an overview of our research activities in the Lighthouse. So we start with the first working group on MRI lesion tracking. And I cannot help myself. I still want to talk a little bit about radiotherapy. So In our clinic, when we want to treat a lung cancer patient, right, we have to account for the motion during the delivery of the radiation because the patients do need to keep breathing. And so here what you can see is that instead of delineating a nice gross tumor volume, GTV, around the lesion, we have to delineate an envelope. So this is the larger red volume, which is called the internal target volume. And we will irradiate this entire region. So this is good for treating the tumor with the high enough dose, but unfortunately, we impact more healthy tissue, and this is detrimental to the patient. Instead, what we can do is use the MR-Linac. So here, we can use the Cine MRI that I told you about, right? We image a plane of the patient continuously, and we can follow where the tumor is in red. And when it's in the right place, in this yellow area, we switch the beam off. Otherwise, we switch it off. So as you can see here in the diagram, this gives us a much more conformal irradiation. The problem is that the beam is often off, and so the patient has to lay there much longer, and we can process or treat less patients per day because of the extended treatment time due to all these beam off moments. And so what we want to do is to increase the efficiency of this treatment with tumor tracking, right? I alluded to this a little bit earlier. We have Cine MRI. We want to track the tumor in real time, see exactly how it's moving. And then we don't want to gate the treatment, but we want to use the collimators available on these machines to actually follow the lesion in real time. So this is called multi-leaf collimator tracking. So you see a demonstration here with an object where instead of sending radiation, we have like a light field showing the shape of the collimator, showing us that we can follow this moving lesion. Of course, here this is very simplified setting. We want to do this in the case of real world patients. And so we need accurate and fast tumor tracking on Cine MRI. And so these are activities that were supported by the Lighthouse. So besides our own research group activities, we organized a data challenge ourselves at the MICAI conference last year, which was called TrackRad. And so in TrackRad, the participants had the task of exactly solving this problem. So following tumors on these Cine MRIs. We wanted to see, after having done our own research on this topic, we had developed a large database of images, and we wanted to see what the community could come up with. And so very briefly, we amassed a total of 2.8 million Cine MRI images from 6 international MR-Linac centers. So this was beyond the BZKF. And this was all made public for participants to train on. And then we had an MR-Linac manufacturer, Electa, sponsoring the prizes. And here we have the happy winners of the conference. And so I want to talk about like what we learned from that challenge. And so here you can see the 5 top teams and their dissimilarity score on how well their model's prediction matches the tumor for the whole sequence of Cine MRIs. And you can see that we have very high dice scores, right? They're even higher than what I showed you earlier for the pancreatic tumors. And another thing we notice is that all of them use this variant of this SAM, right? This segment anything model. So all of them use foundation models again. So you can see there's a trend that foundation models are really an elegant solution to our problems. If we compare the results to the variability between observers, we again find exactly the same performance. So the models are performing at the same level as our observers. And then the run times, this is also important for this application, are very fast as well. And so if you're interested, you can quickly, the winning entry, they use MedSam2, so a medical version of the segment anything model, and they fine-tuned it on the data we released to make it even more performant on the task. And so now we're moving kind of beyond respiratory motion. So the data in the challenge was mostly breathing motion. And now we want to tackle in the Lighthouse project the irradiation of the beating heart or lesions close to it, so cardiorespiratory motion. And this is a much more challenging case because we have 2 motions coupled, one of them at a very high frequency. This typically involves patients who may have sarcomas very close to the heart, Or outside of oncology, we are beginning to treat ventricular tachycardia cases. So this is where there's a myocardial scar, which is causing life-threatening arrhythmias, which can be ablated with radiation therapy. And so for both of these applications, we're developing mRNA workflows, which are able to irradiate the beating heart by moving the radiation beam in synchrony. And here we have some challenges because the time it takes to move these collimators is about 300 milliseconds. And so in 300 milliseconds, your heart has moved away from where it was initially. And so for this, we need faster imaging. So this is the project of Olaf Dietrich and his PhD student, Beatrice Villata, who are accelerating MRI reconstruction by using machine learning methods. So they combine undersampling strategies in the case space with machine learning to restore the full image quality. And then in my group, we have Nicolas Münchlegel, who's, I want to play this video again, who's working on tracking the beating heart on CNA MRI at 11 hertz and predicting the motion with predictive models that we train on these data sets. And so this is going very nicely for Nicolas. In Erlangen, we have the project P2. Now we're moving more to like a little bit more stationary imaging. And so the idea is to explore the use of low field MRI scanners. So there's a new generation of scanners operating at 0.55 Tesla from Siemens, which are very interesting for local therapies because they're very easily installed in, let's say, non-radiology settings. So they require much less, let's say, shielding and so on. And so the installation is easier. And so the guys in Erlangen are working on developing a series of MRI protocols to quantify the motility in the bowels, to map lesions with T2 mapping and with diffusion imaging. And they have a specific focus on rectal cancer patients to determine therapy response based on this multi-MRI type of characterization of the lesion. They are also working on interesting things with motion. So decoupling motion in the abdomen from respiration and peristalsis, which is quite interesting for the applications that we have at our MR-Linac. I see that I will need to speed up a little bit. So moving to the second working group on multimodal characterization. We have a project led by Jan Picken at the Technical University, focusing on esophageal cancer. So as you can see, this type of cancer is not necessarily one of the very top in terms of incidence, but unfortunately, the mortality is rather high. And so 5-year survival is only 20%. And it's strongly believed that better personalization would improve treatment. And so Jan is proposing a pretty novel multimodal approach. So to gather imaging prior to treatment, not only the classical radiotherapy computed tomography images, but also histological imaging and endoscopic imaging, which is actually quite novel. So this has not been tested much before, and combine all of them into a multimodal predictive model. And then here we're really relying on the benefits of having a BZKF wide network. So you can see that we managed to generate a data set which is almost twice as big as what Jan had access to in his institute, by leveraging contributions from every center. And here the Lighthouse and the BZKF were crucial for this. We could benefit from the help of the data sharing lawyer of the BZKF, Ms. Rebecca Kieser, who advised us on how to set up a study protocol and set up contracts for data sharing between the entire network. And this was very smooth. And so now data collection is almost finished. And the guys plan to use, again, foundation models to generate features that they will use to predict the outcomes of the patients. In Würzburg, similar activities are going on around endoscopic imaging. So endoscopy is a bit further away from my specialty, but Professor Han explained to me that when they do endoscopy, if they observe a cancerous lesion, typically their job is over, and they're very sorry to see that, and they have to, the patient has to undergo a biopsy, and then it takes quite some time until they can determine the invasiveness of the cancer. And this is all to do with, in colorectal cancer, this is related to microsatellite infiltration. Whether this is happening or not will determine the prognosis. And they're working on an AI tool which can immediately determine the status based on the endoscopic images. And so they have collected also a very large data set. In this case, it's more like pan-German. So they have data internally and from Charité in Heidelberg, and they can demonstrate very good performance of this model. Maybe a note to anybody in the audience interested, we're definitely open to adding additional BZKF data sets. So if you can speak to your endoscopist, I think this would be appreciated. And here they can also distinguish like where the models are focusing their attention in this colorectal cancer image taken from the endoscope, how the model is basing the decision, which helps with explainability. Okay, the final pillar is on surgical guidance. And here in Augsburg, Professor Wendler is using novel pressure sensors integrated at the CT scanner, coupled with optical imaging for determining the surface to basically estimate how the patient is laying at the time of imaging. And then by having the same hardware in the intervention suite, how they are laying just before, for example, surgery or other interventions. And the idea here is to basically update the anatomical model of the patient to better guide surgeons or interventional radiologists in their tasks. And they propose to use some machine learning approach that combines very cleverly these different inputs to update the pose of the patient. So they have a clinical study running. They will collect 2,000 CT scans of patients with the mat and the camera present, acquiring data as a data generation effort, and they're working on these machine learning approaches. And finally, in Regensburg, they are working very closely with Augsburg in analyzing during surgery, the liver is exposed, and an image with an ultrasound while there's contrast agent. And by characterizing the dynamics, we're able to determine where's the margin, for example, of the lesion. And this can help them guide therapy decisions in the course of the surgery. So this is really, let's say, real-time image guidance happening. Okay, I just want to quickly talk about also affiliated projects. So the first 7 projects were present at the foundation of the Lighthouse. In the last year, we also expanded our activities in the BZKF. So we have affiliated projects. So one of them is from Dr. Christian Heiliger, who's working also in surgery, but more at the level of augmented reality. So if I play this video, they are kind of overlaying, for example, important vessels in the view of the surgeon while doing this robotic surgery. And so this lets them guide the surgeon. And they explained to me that this is particularly important with surgeons who are beginning or in training to provide this type of information. Our other affiliated project is with Dr. Florian Hinterwinner from the TU, who's part of the BZKF study group for bone sarcomas. So this is a newly funded study group, which works very closely with our Lighthouse to provide AI image analysis of bone sarcoma imaging. And so we're just kicking off our activities together. Okay, I will try to go quickly through my last slides. And so I want to talk a little bit about the outlook for this group. So what we aim to do is to we not only want to push, let's say, the science of image guidance forward, but we also want to bring benefits to patients. And so for us, it's very important to test our developments in clinical studies. And we also want to institutionalize knowledge of how we perform this translation of AI solutions that we develop in the lab or adapt to something which is clinically applicable. And so the objective of our Lighthouse long-term is to achieve the clinical use of AI-based image guidance solutions. We want to improve the precision of local therapies, and we want to position Bavaria as an international leader in this field. I think the example of this core project can serve as a good template for our pipeline. So we want to start from computer science model developments or other technological development, not necessarily AI. They don't necessarily need to come from the Lighthouse, but they can. We want to translate that to the clinic for evaluation to generate evidence of the value, and eventually generate like study protocols where we can prospectively get final confirmation of the value of these developments. And so we see three phases in our Lighthouse. We're currently in phase one, so this is the first 2 years of our activities. We're currently in the second one of those years. This is where we're developing basic capabilities in AI and image guidance. In the second phase, we want to select these developments which are the most promising and test them against the real world. So prospective validation, as I explained earlier. And finally, in the third phase, we hope to move further in this translation, possibly having generated enough expertise and evidence to move towards adopting some of these more successful methods, providing regulatory support and testing in the BZKF prospective trials. So to summarize, our Lighthouse is open to collaborations within the BZKF. We support research projects. We also are building links to industry in Bavaria. We offer AI-supported segmentation tools, image processing expertise, and also know-how for image-based data sharing within the BZKF. So I would like to encourage you to contact us if any of these areas interest you. And finally, I'd like to thank you for your attention. I would also like to thank the BZKF for giving me the opportunity to lead this group and also for letting us set up this very great collaboration. So you can see everybody from the Lighthouse here at our retreat in Bayern, Greece, near the center of Bavaria, where we discussed how this vision that I presented should evolve.